Chemistry is the subject of combining ingredients or elements by rearranging their electrons to form molecules, liberating and trapping energy in various ways. An element is transmutable into another element only by the processes of fission or fusion. Chemistry is simply rearranging the electrons in elements and combining them in different ways. A lot of the low-temperature universe involves chemical reactions, as do a lot of the phenomena on the Earth. But if we're asking about the chemistry of the universe, the most interesting thing to ask is, what is the universe made of in terms of chemical ingredients? We'll tell this story more fully when we talk about the life and death of stars. But to see why it's an interesting question to ask, let's just look at what the universe is made of. If you take the Sun, which is indeed a typical star, we'll see that by mass, 90% or more of the Sun is made of hydrogen, and most of the rest is helium, the two simplest chemical elements. All the rest of the elements is less than 1% of the mass of the Sun. And in particular, carbon, nitrogen, and oxygen, which turn out to be very important for biological material, are trace ingredients. By contrast, humans, or any living creature, are composed of roughly 2 parts to 1 oxygen and hydrogen in the form of water, and about 10 or 11 or 12% carbon, depending on the creature. Other ingredients, like nitrogen, are trace. Life depends on roughly 12 or 15 different chemical ingredients. Notice that the proportions of those elements are completely different in life stuff than they are in star stuff. Most of the universe is composed of the simplest 2 elements, hydrogen and helium, in roughly the same proportions they are in the Sun. Clearly, in biological material, something different is going on. If, instead, we look at the rocky objects that surround a star, the planets, with our Earth as a typical example, we see that the chemical constituents are different again. The Earth contains almost half oxygen and half of the rest silicon, with aluminum and other metals also quite abundant. That's the Earth crust. In the core of the Earth, it's nickel and iron, 2 metals. So the rocky material of planets is based on quite different ingredients than the Sun itself, or even than humans. Where did these chemical ingredients come from that lead to the very different chemistry of a planet and a star and a person? To get a sense of the relative abundance in the universe of the different chemical ingredients, the elements in the periodic table, let's use the analogy of decks of cards. If we had a deck of cards of a typical sample of the universe, which is to say star stuff, or what the Sun or any other star like it is made of, we'd find that most of the cards are cards that represent hydrogen or helium. We can imagine the numbered cards to be the hydrogen atoms and the face cards to be the helium atoms. It's a remarkable thought, and something that we'll talk about more when we discuss stars and cosmology, that the universe is 1/4 helium by mass. What about carbon, upon which life on Earth, and we imagine life elsewhere in the universe, is based? Carbon is a predicate for biology because it makes a universal toolkit of building complex molecules, long and perhaps infinite chains of complexity required for biology to function. Carbon is actually a trace ingredient in the universe as a whole. In the deck of card analogy, you'd have to inspect 60 decks of cards to find the first card representing a carbon atom. Virtually all of the rest would be hydrogen and helium. Heavier and heavier chemical elements are correspondingly rarer, and if we go up to a heavy metal like gold or platinum or silver, these atoms are remarkably rare in the universe as a whole, as indicated by star stuff. In this analogy, see the building here, a modern architectural cube somewhere in Germany. You can see the human for scale. If you fill this entire cube with decks of cards, on average only one of the cards among the many, many decks of cards would have a gold atom. Gold is phenomenally rare, as are other precious metals in the universe. The elements we see this way were made by stars. It's remarkable they exist at all. Remember, the universe is overwhelmingly the 2 simplest elements, hydrogen and helium. As a precursor to talking about stars and the creation and dispersal of heavy elements, let's give the story of the gold atom you might find, perhaps one in a ring on your finger or in an earring. Where did that come from? It was not present at the creation of the universe. The Big Bang consisted of primordial material, subatomic particles, pure and simple. There was some helium made in the Big Bang, but almost no heavier elements. So we have to depend on a history that takes billions of years and plays out over space and time, where heavy stars were able to generate elements up through the periodic table by sequential processes of fusion. At the end of their lives, they dispersed these heavy elements out into space, either by ejecting envelopes of gas late in their life or by violent detonation in a supernova at the very end of their life. To get all the way up to gold, it might actually take sequential generations of stars. Perhaps in the first set of fusion processes only carbon is produced, and then that carbon atom must become part of the core of another star to ascend the fusion chain up to iron, or then gold. A gold atom, a particular gold atom, might have gone through a number of fusion cycles and been ejected into space several times. Eventually, the gold atom is floating in interstellar space to become part of a nebula that would one day form a star and planets, including the Earth. By natural processes, the gold atom finds itself at the cool outskirts of this nebula and is swept along with other rocky materials involving silicon and oxygen into a rocky object, a terrestrial planet. The last part of this gold atom's journey takes 4.5 billion years, because that gold atom must have pre-existed the formation of the Earth that long ago. The gold atom is mixed in with other similar and dissimilar atoms in the geological context of a living planet, churning through magma cycles up and down in the crust and mantle. And for it to end up in our possession in the modern age, it must have at some point been distilled enough to shine and reach towards the surface, where it might be eroded by a water running or be dug out by a miner, to become part of the human story. The extraordinary story of gold is a story that involves astrophysics and space and time extending over light years and billions of years. So the exchange of a ring between two people has a resonance beyond its emotional resonance. It involves a deep and profound and exciting story of astrophysics. When we talk about chemistry, that is the subject that involves the rearrangement of electrons in elements to form different combinations. But in astronomy and astrophysics, chemistry has a different meaning. It involves the creation and dispersal of elements inside stars. We can see that this must have taken place by looking at star stuff, the composition of a typical star, which is almost entirely hydrogen and helium, the two simplest elements, with the stuff that humans are made of, or that the planet we're standing is made of, which involves relatively larger amounts, 10 or 20 times more, of carbon, nitrogen, and oxygen, and metals. Even though they are very rare, these metals and life-bearing elements were created inside the cores of stars, dispersed into space to become part of our story. This is a story we'll tell more fully when we consider the evolution of stars.